So hello everyone, welcome back to another video on discrete maths. So we were doing this topic called relation. Let us continue with that topic. Alright, so in the last video we ended the last video by looking at a theorem. It said that the relation R on a set A, right? Set A is transitive if and only if R to the power n is a subset of R for n equal to all this 1, 2, 3 integers. Okay, so this is the theorem that we looked at in the last video. Alright, the relation R on a set A is transitive if and only if R to the power n is a subset of R for n equal to 1, 2, 3, that is n being a integer, positive integer. Alright, so let us now go ahead and prove this theorem. Okay, so this is a if and only if theorem. So this is a bidirectional theorem, biconditional theorem. Alright, so we have to prove both this P implies Q and Q implies P. That is, we have to prove that if R is this relation R on set A is transitive, then this condition holds, and if this condition holds, then this is transitive. Let us prove the other way first, that if this condition holds, then this is transitive. Alright, and this is a very simple observation that we are going to make. Alright, let us say I have this AB belongs to R and I have this BC, this also belongs to R. Alright, so I have both of this, let's say I have this 2. Okay, then what does this mean? By definition of R square, I know that by definition of R square, I know if these 2 belongs to R, then the composition of R and R, this would belong to the composition of R and R. Right? So AB, BC. So AC would belong to R square. Now R square, I know, is a subset of R. Why do we know? Because we are trying to prove that if R to the power n is a subset of R, then R is transitive. Okay. Now we know if this belongs to R, then this belongs to R square. Okay. So we have been given that this is true. Now what do we know? That if this and this belongs to R, then this also belongs to R. Why? Because this belongs to R square and R square is a subset of R. So for that reason we know that this also belongs to R. Okay. So that is how we have shown by looking only at R square. We are not going to look further. Okay. Looking at R square is sufficient. We know that R is transitive. Okay. So we have shown that if this is true, then R is transitive. How did we show that? We have shown it by showing that if this and this belongs to R, then AC also belongs to R. Okay. So that is the definition of transitive. If AB and BC belongs to R, then AC would also belong to R. That is the definition of transitive. Okay. So we have assumed this 2 belongs to R, then this would belong to R square. Right? This is by definition of R square. Now since R square is a subset of R, so we know AC belongs to R. So that is how I know that if this 2 belongs to R, then AC belongs to R. Okay, that is how we have shown that R is transitive. Okay, because this belongs to R square and R square is a subset of R, so this belongs to R. Okay, this is simple. This one direction. Let us try to look at the other direction. That if R is transitive, then R to the power n belongs to R. Now we are going to do this by induction. Alright, so we are going to have this base case. If n is equal to 1, then what is R to the power n? R to the power n is R to the power 1, that is 1. We know this by definition of power. Okay, in the last video we talked about what is the definition of power. It was a recursive definition. It said that r to the power 1 is r. So if n equal to 1, then r to the power 1, that is r. R is a subset of R, right? We know that by definition of subset. So lots of definitions are giving us all these requirements for this proof. All these axioms are given by definition. Alright. So if n equal to 1, then trivially true. Because r to the power 1, that is R, is a subset of R. Okay. Now this is the base of our induction. Let us now have this inductive hypothesis. Okay. Let us assume Rn is a subset of R. Okay. For some positive integer n. For positive integer n. So what do we have to prove? We have to prove that R n plus 1 is a subset of R. Alright. Now let us assume that there is some AB that belongs to R n plus 1. Alright. Now what does this mean? This means that this AB belongs to Rn compose R. Alright. Now AB belongs to Rn compose R. What does that mean? Okay. So this means that there is some X such that not Rn compose R, R compose Rn. Alright. So this is spelled the other direction. R compose Rn is written like this. Rn this symbol and then R. Okay. So there is this some X. Since AB belongs to this, there must be some X such that X belongs to R and XB belongs to R to the power n. Alright. This is what composition means. Right. If AB belongs to this R compose Rn, then there must be some X such that AX belongs to R and then XB belongs to Rn. Only then AX and XB will compose and we will get AB that we assumed belongs to Rn. Right. Rn plus 1. Now, what do we know? What are all the things that belongs to R? Okay. We know AX belongs to R. Right? We know this from here. And since Rn is a subset of R that we had in our inductive hypothesis, right? That was the assumption in inductive hypothesis. So Rn is a subset of R. So this also belongs to R. Correct? Think about it. What was our inductive hypothesis? Our inductive hypothesis said that Rn is a subset of R. Okay. Then we assume that AB belongs to Rn plus 1. So there must be some AX that belongs to R and there is some XB that belongs to Rn. Since Rn is a subset of R, so this XB would also belong to R. Correct? Now, see, if I have this and if I have this in R, and what is given? R is transitive. Okay. So what does that mean? That means AB also belongs to R. Okay. So we had taken this AB that we assume to be in Rn plus 1, R to the power n plus 1, and we have shown that that AB would belong to R. Okay. Take any AB that belongs to R n plus 1. We have shown by inductive hypothesis that by induction that AB would belong to R. Okay. So that is how we have shown that all this AB that belongs to Rn plus 1 would belong to R. In other words, we have shown that Rn plus 1, everything in Rn plus 1 belongs to R. In other words, Rn plus 1 is a subset of R. So that is how we have shown that if R is transitive, then Rn means R to the power n is a subset of R by induction. Okay, and the other direction also we showed previously. Okay, so this is how we have proved this theorem. Okay, so this theorem, the proof is fairly easy. The forward direction we proved by this construction, that if AB belongs to R and BC belongs to R, then AC belongs to R square. Okay, and since R square is a subset of R, so AC would belong to R. And this direction, that if this is true, then this is true, that we had shown in that manner, and if this is true, then this is true, we have shown by induction. Okay, so that completes our proof. Alright. Okay. Next, let us try to talk about this representation of relation. We already talked about this matrix representation of relation, right? So let us look at that with an example. This topic is representation of relation. Okay, first we are going to look at this matrix representation. Let us say I have a set A and it has 1, 2, 3, and I have this set B, it has 1, 2. Alright, so let us define the relation R. It says it has all this A, B such that A belongs to the set A, B belongs to the set B, and A is greater than B. Alright, so what will be in this relation? This relation will contain the ordered pairs. 1, 1, is 1 greater than 1? No, it's not. So 1, 1 will not be there. 2, 1, is 2 greater than 1? Yes, 2 is greater than 1. So 2, 1 would belong to the relation. Is 3 greater than 1? Yes, 3 is greater than 1. 3, 1 will belong to the relation. Is 3 greater than 2? Yes, 3 is greater than 2. So 3, 2 will belong to the relation. Is 2 greater than 2? 2 is not greater than 2. 2 and 2 are equal. So 2, 2 will not belong to the relation. These are all the ordered pairs that will belong to the relation. Alright. Now let us represent this using a matrix. Okay. So along the rows we will have three rows and 2 columns. Okay. So 1, 1 does not belong. 1, 2 does not belong. 2, 1 belongs. 2, 2 does not belong. 3, 1 belongs. 3, 2 belongs. Alright. So this is how we represent this relation in a matrix form. Right. So this is 1, 2, 3. Set A is over here. We don't need to write this. Alright. I am just showing you. So set 1, set A. This 1, 2, 3 is over here. Set B is in this, along these columns. Okay, 1, 2. And this is the matrix representation. Let us now look at another simple thing. Let us say my set A is A1, A2, A3. Alright. And my set B is B1, B2, B3, B4 and B5. Alright. And say this is my matrix representation. 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0 and 0, 0, 1. Alright. So what are all the ordered pairs that are in the relation? This is the question. So let us try to find out. Okay, this is said a matrix for representing relation R. So R will contain what? It contains this A1, B2. Okay. If you have confusion regarding what these are, then you can write down. But write it in rough. Okay. Don't write it in your answer. So along the columns I have this set B. Along the rows I have this set A. So I have A1, B2. Alright, over here. Then I have A2, B1. I have A2, B3, A2, B4. Okay. Then I have A3, B1, A3, B3 and A3, B5. So this is what I know. These two sets are given and this relation is given in this matrix representation. From this relation I know if there is a 1, then this A2, B1 would belong to my relation. Alright. So from this matrix representation I can get down to this set representation. Alright. So yeah, that is something we have. Now let us look at these properties that we have. Right, this reflexive, symmetric, antisymmetric. Let us look at this relation. Okay, let us look at this relation. Is this relation symmetric? Reflexive, symmetric and antisymmetric. These are three questions that we have. Alright. So is this reflexive? A is there, one say whatever the set name is. This A is there, this CC is there, but BB is not there, right? So it is not reflexive. Is it symmetric? See over here, I have this 1 in here and a 0 in here. Okay, this position is 2, 3, right? So in 2, 3 I have 0, in 3, 2 I have 1. So this is not symmetric. Is it antisymmetric? See over here, this 2, 1 is 1 and 1, 2 is 1. So 2, 1 and 1, 2, both of them are 1, but 1 is not equal to 2, right? So because of that reason we know this is not antisymmetric. Now let me make some changes in this matrix. Alright. What about now? Is it reflexive? Along the diagonals all of them are 1. Okay, so it is reflexive. Is it symmetric? So in both these mirror places I have 1 and 1, I have 1 and 1 and I have 0 and 0. So all this ij is equal to ji, right? So because of that reason we know this is symmetric. Is it antisymmetric? See, this 3 2 this 2 3 2 and this 2 3, both of them are 1, but 3 is not equal to 2. So we know this is not antisymmetric. Okay. Okay. So one thing you should know, in case of symmetry, if we take this matrix and then take the mirror image over here, they should be the same. Alright. In other words, for some relations say R, if I have this matrix representation MR, okay, this should be equal to MR transpose. Okay. If this is true, then my relation is symmetric. Alright. So next, let us look at the set operation, union and intersection. Alright. So I hope you got this. How to find whether some relation is reflexive, symmetric and antisymmetric by looking at the matrix representation. Alright. let us say I have this matrix representing relation R1, and this is 1 0 1 1 0 0 and 0 1 0, and I have another relation R2, and this is the matrix representation. Okay, 1 0 1 0 1 1 and 1 0 0. Alright, so here is the question: what is the matrix representation of R1 union R2, and what is the matrix representation of relation R1 intersection R2? Okay, so we already talked about this. We can do this union intersection of relation because relation are essentially sets. So all these set operations that we have, we can do this. Okay, so we can do this union and intersection. So I have this R1 and R2, these two relation represented in this matrix form. I want to find the union and the intersection. It is very easy. What do I have to do? I have to do this position wise. Okay, or in case of union, and a position wise and in case of intersection. So let us go ahead and do that. Okay, so we will do or of this position and this position. These two are what? 1 or 1 is 1, 0 or 0 is 0, 1 or 1 is 1. So I am talking about this conjunction disjunction, right? Or and this thing that we have in Boolean algebra. Okay, this 1 or 0 is 1, 0 or 1 is 1, 0 or 1 is 1, then 0 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0. Alright, so this is what I have. This is the matrix representing this union of these two relations, R1 union R2. So R1 union R2, that will also be a relation. This is the matrix representation of that relation, R1 union R2. Alright, so let us next look at this relation, R1 intersection R2. So this relation we have, R1 and R2, their intersection will also be a relation. So let us look at the matrix representation of that relation. So previously we did union, and we did union how? By taking this position wise or, right? Now we will do this position wise and to find intersection. Okay, so 1 and 1 is 1, 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, 0 and 0 is 0 and 1 is 0, 0 and 1 is 0, 0 and 1 once again 0, 1 and 0 is 0, and 0 and 0 is 0. Alright, so this, by doing this position wise and we are getting this matrix. So in this union, what did we do? To find some position ij, we did the OR of this matrix ij and this matrix ij. Alright, to find some position ij in AND, we did the position wise AND of ij in here and ij in here. So that is how we got this intersection, and this is how we got this union. Okay, so simple. Next, this is also simple, but pay attention. All right. We are going to find composition of R and S, written S before and R after that. How will we find that? We will find that by first taking matrix R. This is S, R compose S, written as this operation R. We will take this matrix R and we will do something called binary product with matrix S. Okay. So let us go ahead and try that with an example. Let us say I have this matrix R. It is represented as 101, 110, this relation R, 000. Alright, and then we have this relation S represented as 010, 001 and 101. Alright, so let us try to find M R compose S. What are we going to do? We are going to do something called binary product. Okay, binary product is like your normal multiplication, right? Matrix multiplication. Just the difference is that previously when we multiplied, now we are going to do an and previously when we did an addition, now we are going to do an OR. Okay, so let us go ahead and write down in the normal way. We will first take this column and we will do it that. So it is 0 into 1 plus 0 into 0 plus 1 into 1. Okay, then 0 into 1 plus 0 into 1 plus 1 into 0. Then 0 into 0 plus 0 into 0 plus 1 into 0. Okay, then we will take this column, of course, like in normal matrix multiplication 1 0 0. I will have 1 into 1 plus 0 into 0 plus 0 into 1. Okay, then 1 into 1 plus 0 into 1 plus 0 into 0. Then 1 into 0 plus 0 into 0 plus 0 into 0. Okay, finally I will take the third column. Third column is 0 1 1. This will give me 0 into 1 plus 1 into 0 plus 1 into 1. Then 0 into 1 plus 1 into 1 plus 1 into 0. Then 0 into 0 plus 1 into 0 plus 1 into 0. Okay. So this is what I have. Alright. So what are we going to do? We are going to do the end of these two. Right? End of these two. And end of these two. And then we will go, what will be the end of these two? It will be 0. This 2 will give me 0. And this 1 and 1 will give me 1. So 0 or 1 will give me 1. Alright. Similarly, 0 and 1 will give me 0. 0 and 1 will give me 0. 1 and 0 will give me 0. So 0 or 0 will give me 0. Here also 0 or 0 will give me 0. Here 1 and 1 is giving me 1. 0 and 0 is giving me 0. 0 and 1 is giving me 0. So 1 or 0 is giving me 1. Here also I will have a 1. Here I will have a 0. Alright. In that same way, here I will have a 1. Here I will have a 1. Because of this I will have a 1 over here. Because of this I will have a 1 over here. And here I will have a 0. Alright. So yeah, this is the matrix representation of this R compose S. Alright. Once again, I want to draw your attention to this thing. R compose S is the multiplication of this matrix with R matrix with S matrix. Okay. S is written before, R is written afterwards in composition. So R will come before and S will come later in the multiplication. Don't mess this up. Okay. This formula R compose S is R into S, not S into R. Okay. So observe this. Be sure that you don't mess this thing up. Alright. So this is what we have. Next, let us say I have this relation MR. This relation R that is represented using this matrix MR 0 1 0 0 1 1 and 1 0 0. Okay, say I want to find MR square. Okay, what am I going to do? I am going to multiply this matrix with itself. Okay, I am not going to spend too much time. Observe one thing, you have to multiply this matrix with itself, right? Now I want you to observe one thing. I can do this very fast. Okay, I don't need to write down everything that I did before in the last example. This column I am going to do this matrix multiplication, right? I am going to do 0 1 0, then 0 1 1 into 1 0 0 into 0 1 0 0 1 1 1 0 0. Okay, I am going to multiply these two matrices. Okay, now this is not normal multiplication where I have to add and multiply. Okay, this is Boolean multiplication where I have to do this and or. Okay, now I will take this first column 0 0 1 and I will do this multiplication, do this and, right? The 0 and 0, 1 and 0, 0 and 1. So make this observation. This 0 and 1, since they are being ended with this 0 and 0, they will go away. Okay, they will become 0. So only way how this can be 1 is if I have this 1 and whatever I have, only then it is going to be a 1. Right? This 1 and 0 will give me 0. But in the second position, I will have this 1 and 1 and that will give me a 1. This 0 and this 0 will remove these things. Right? So I will have only this column that can give me a 1. So what I mean is this. In my first column, I am going to have 0, 1, 0. Okay. Then I will take this column, right, from this matrix, this 1, 1, 0. Now this column cannot contribute to my OR because this is going to be 0. When I multiply all this with 0, these are all going to be 0. So only way I can get is from these two columns. So if one of them is 1, okay, then this 1 and 1 is going to give me a 1 and my value is going to become a 1 over here, right? So all these 3 will become 1. These 2 will be ended and become 1. And when I OR with other things, this will become 1. These 2 will be ended and become 1. And when I OR with other things, this will become 1. Similarly, these 2 will become 1. And when I OR with other things, this will become 1. Alright. Then let us multiply with the last one. 0, 1, 0. And this is going to be 1, 1, 0. Okay. So, yeah. This is the matrix representation of R square. Now, if you have any confusion regarding what I just said, okay, then go ahead and use the method that we used in the last example. Okay, but if you understood this, this is going to be very useful. This is going to speed up your calculation. Alright, and even in the previous example, you can apply this method. Alright, you don't need to explicitly multiply. When I say multiply, I mean AND. When I say add, I am meaning OR. Right? You don't need to explicitly multiply everything. See, this 0 and all this is going to give me 0. So only thing that is going to remain is this column. So this column I can substitute directly over here. Or in case of when I multiplied with this column, I took over here. These two were 1. This is not going to contribute anything. So this 0 will, all of this will become 0 when I multiply with this 0. So only thing that will contribute are this. So if any of this is 1, I will have a 1 over here, right? So yeah. So alright, this is how I have R square. If I had to find R cube, what will I do? R cube would have been R cube is, sorry, the matrix representation of R cube. Let me write this. Okay. So this would be R square. R cube is what? R cube is matrix R square compose R. Means R compose R square, sorry. So this will be matrix R Boolean multiplied with matrix R square, right? So this will be this matrix 0 1 0 0 1 1 and 1 0 0 multiplied with this matrix. This is my matrix for R square. Alright, so this is 0 1 1 1 1 1 0 1 0. Alright, so this, let me do first. 1 1 0, since only this column is going to come 0 1 0. Okay, then over here I will take from any of them. Okay, so if anything has a 1, since all of them are 1, so if anything has a 1, I will take 1. So then next one is 1 1 0, so I will take these two. If anything in these two column is a 1, then I will write a 1 over here. 1 1 1. Okay, so yeah, this is my matrix representation of R cube. So in this way we can go ahead and find R4, R5 and so on. Okay, so this was your matrix representation of relation. Okay, and then we learn how to do this operation union, and then we learn how to do interaction, and then this composition. Alright, composition of relation using this representation. So in case in exam, okay, they give you a very long set representation, okay, and ask you to find composition of two very long say sets, okay, set representation of relation. So you may spend a lot of time in that, but if you do this, it will be very fast. Okay, so think about it. If you are asked to do that, you can bring it to this form, solve it, and take it back to that form. That will be speedier, in my opinion. Okay, anyway, if you are comfortable with that, then go ahead and use that, not a problem, but this is easier. Okay, okay, the next representation that we are going to see, and this is also a easy representation. This is the directed graph representation. Okay, a directed graph will have vertices, okay, and edges. So a graph has vertices and edges. The difference between a normal graph and a directed graph is that in directed graph these edges have a direction. Okay, so we will see what directed graphs are. Let us look at them. Let us look at one of them with an example. Let us say I have this relation R on this set 1 2 3 4, and this relation is given by 1 1 1 3 2 1 2 3 2 4 3 1 3 2 and 4 1. Alright, so let us say this is my relation. I am going to represent this using a directed graph. So my set, I did not tell you about the set. Set has 4 elements, 1 2 3 and 4. So how am I going to draw the graph? Okay, I will have these 4 elements, 1 2 3 4. This is a 1, this is 2, this is 3, and this is 4. Now each of them, I have 1 1, so I have a edge from 1 to 1. Alright, then I have 1 3, so I will have a directed edge from 1 to 3. Okay, so these edges will have direction. All these elements of the set will be vertices in my graph. Alright, so these 4 vertices I have, and these directed edges I have. Then 2 1 is here. Okay, so I can draw like this. Then 2 3 is here, so I will draw this. Then 2 4 is here, so I will draw this. And of course I have to give edges, because this 2 4 is here. Okay, if I don't give direction, then I will not know whether 2 4 is here or 4 2 is here. So this direction will tell me that 2 4 is here. Okay, then 3 1. So I have this 1 3, and also I have this 3 1. Okay, then 3 2, then 4 1. Okay, here is my question: uh, is this reflexive? Okay, so I can see there is this self loop. That means 1 1 is here, but there is no self loop over here. 2 2 is not here, 3 3 is not here, 4 4 is not here. So I know this is not reflexive. Is it symmetric? See, I have this edge 2 1 over here. Okay, this is 1. I have this edge 2 1 over here, but 1 2 is not here. Okay, so this is not reflexive. Is this antisymmetric? I have 1 3 and 3 1, both of them are here, but 1 is not equal to 3, right? So this is not antisymmetric. Is this transitive? That we have to figure out. Okay, I have this 4 1 and I have this 1 3, right? I have 4 1 and I have 1 3, but I don't have 4 3, right? So because of that we know this is not transitive. Okay, yeah. So yeah, this is what we have. One relation that we have represented in using this directed graph, digraph. Okay, let me represent another relation. Okay, using directed graph. So this is 1, this is 2, this is 3, this is 4. Okay. Okay. Now here is the question. What are all the ordered pairs that are in this relation? Let us try to figure out. Okay. So 1 2, is it there? 1 1, is it there? There is no self loop, so 1 1 is not there. Is 1 2 there? No. 2 1 is there. Okay, this H means that 2 1 is there, 1 2 is not there. What about 1 3? Yeah, 1 3 is there. What about 1 4? 1 4 is there. Okay, now 2 2, is 2 2 there? Yes, there is this self loop, so 2 2 is there. Okay, what about 2 3? Yeah, this H, they say that 2 3 is there. What about 2 4? 2 4 is not there. Okay, 2 4 is not there. Alright, then 2 1 is there. Okay, so 2 1 is there. Then 3 3 is here, because of this self loop we know 3 3 is here. Then 3 2 is not there, right? So 2 3 is there, 3 2 is not there. 3 1 is there. Okay, and what about 3 4? 3 4 is also not there, 4 3 is there. Now let us look at 4. 4 1 is there, correct? 4 2 is not there, 4 3 is there. Because of this edge we know 4 3 is there. What about 4 4? This self loop is not there, so 4 4 is not there. So this is our relation. I have 9 edges, 1 2 3 4 5 6 7 8 9, and I should have 9 ordered pairs over here. 1 2 3 4 5 6 7 8 9. Yeah, so yeah, this is what I have. This digraph representation gives me this relation. Okay, alright. So yeah, asking these questions: is this transitive? Is this let us go systematically. Is this reflexive? So 1 1 is not there. All right. 2 2 is there. 3 3 is there. Okay, sorry. Okay, sorry about that. Yeah, all right. 2 2 is there. 3 3 is there. 1 1 and 4 4 are not there. Okay, so we know this is not reflexive. Is this symmetric? I have this 2 1, but I don't have this 1 2, right? So because of that we know that this is not symmetric. Is this antisymmetric? 1 3 is here, 3 1 is here, right? So 1 3 is here, 3 1 is here, but 1 is not equal to 3. So because of that we know that this is antisymmetric. Alright. And then is this transitive? We have to figure that out. This transitive is a bit time consuming, but then let us go ahead and figure it out. Alright, I have 2 1 and I have 1 4, okay, but I don't have 2 4, okay. So this 2 1 is here, this edge represented by this edge, 1 4 is here represented by this edge, but 2 4 is not here. So because of that we know that this is not transitive, okay. Alright, now let us go ahead and try to figure this for 3 more digraph representation, and then we will be done with this portion. Okay. So this is my digraph 1. Okay. So each of them are they reflexive, symmetric, antisymmetric, and transitive. So is this reflexive? So all these AA, BB, CC or whatever they are called, let us call this ABC. Okay, this AA, BB, CC, all of them are here. So this is reflexive. What about this? This BB, DD, CC, those are here, but AA is not in the relation. So this is not reflexive. What about this? None of them, AA, BB, CC, none of them are here. So this is not reflexive. What about symmetric? AC is there, but CA is not there, right? So this is not symmetric. What about this? All of this, AC is there, CA is here. AD is there, DA is here. AB is there, BA is there. Okay, then this self loop, of course, BB being there means BB being there. So this is symmetric. All this AB means that BA is there. Alright, if there is some XY in here, then Y axis is also here. Alright. What about this? Is this symmetric? AB is there, but BA is not there. So this is not symmetric. Okay. What about antisymmetric? I have this BC and CB. Both of them are here, right? But B is not equal to C. So this is not antisymmetric. What about this? Same reason. AC is there, CA is there, but A is not equal to C. Not antisymmetric. What about this? BC is there, CB is there. This is also not antisymmetry. Alright. Let us look at transitive. Okay. CB is there, BA is there. Right? CB is here, BA is here, but CA is not here. AC is there, but CA is not there. So this is not transitive. Okay. Let us look at this. BA is here, AD is here. So BA, AD, both of them are here, but BD is not here. So this is not transitive. What about this? AB is here, BC is here. Sorry. Previously I had written this, right? AB was here, BC was here, and then AB was there, BC was there, but AC was not there. Okay, that would have meant this is not transitive. But let me make let me change the direction of this edge. Alright. Now let us talk about this. AB is here, BC is here, okay, and AC is there. AC is there, CB is there, AB is there. Alright. So every pair that we have of this form, XY and YZ, we have seen that XZ is there. Alright. So because of that we know this is transitive. Okay. Let me ask you a question. If I remove this edge, what will change? It will still be not transitive, right? So AB is there. Sorry, will it be transitive? Let us go ahead and see. Okay, this will become transitive, right? BA is there, AC is there, so BC is there. Okay, then BC is there, AC does not matter. AC is there, BA is there, that we saw. BC is there. So okay, this one becomes transitive. Is this reflexive? All this AA, BB, CC is there, so this will stay reflexive. Is it symmetry? This AC is there, but CA is not there, so this is not symmetric. Is this antisymmetric? So there is no AB, BC, right? Only case when this AA is there and AA is there. So AA is there, alright. So, but then A is equal to A, right? So this will become antisymmetric, alright. So AB and BA, both of them, when A is not equal to B, both of them does not exist. So this will become antisymmetric. So yeah, this is all about digraph representation. Okay, so we have seen in this video, we started off with the proof that if some relation R on a set A is transitive, then R to the power that will become if and only if R to the power n is a subset of R for all n positive numbers. Okay, we saw that theorem and we proved that. Right. Then we saw two representations of relation. One is this matrix representation, and the other one was this digraph representation. Okay, directed graph representation. So in matrix representation, we saw we talked about these properties, how to find whether this matrix representation is reflexive, symmetric, antisymmetric. Right. We did not talk about transitive, but you can of course go ahead and try that out yourself. Right. And then we saw how to do this union of relation, intersection of relation, and composition of relation using matrix representation. Very simple methods that we saw. Then we saw this digraph, and when doing this digraph, we saw how to find if this representation, this relation represented using a digraph, is that relation symmetric and antisymmetric, then reflexive or transitive. Alright, so we saw all this. Hope you understood everything. You will have questions regarding these topics in your assignment. So if you have any doubt, go ahead, watch this video again, and of course refer to your book, that is Discrete Mathematics and its Application by Kenneth Rosen, is one of the best book on this topic. Okay, go ahead and look at that book. So I hope you understood everything. If not, you can of course WhatsApp me, you can mail me, or you can write your doubt in the comment section below. Thank you for watching this video. In the next video we will be looking at equivalence relation. Alright, so see you in the next video.